All right, so we're back and continuing with our project. So last time we finished off topological sorting, and it worked. Right, we have the test here and stuff. Now we have to add it to the parsing stage. So for that we should write a test for this. And actually this last test would be a good candidate, so it would have to write E first, then it would have to write C, and then A, and you can, yeah, it fails now. Good, so let's just remove the console logs that we had here. That's it. Fix test case and removing console logs. Okay. Cool. I still don't like my implementation very much. I think it's really scuffed. But I want to get a working product before I make the improvements. As long as the test cases pass, I'm happy for now. If they didn't pass, obviously that's a very different thing, but okay. So we're trying to get this pass test to work now. And what we do is in this function, order struct list, where we take nodes and we put them in a graph, right? We take all our structs, put them in a graph, we put the correct edges in as well here. And instead of returning nil, we're going to return the correct thing, which is the reordered array. And again, I'm going to start doing this in a very efficient way, linear searches and all that, but I want the test case to pass, and then I want to refactor in a way that it works. That's kind of my way of developing software, I suppose. You build a case, the test case, you build for it, even in an ugly way. You make sure that your ugly way is still working and is not too different, or at least you don't think it will be too different from the real implementation. And once you have the test cases to fall back on, then you can write a better implementation. You have to be quite strict though, because it's very tempting to stop at the test cases working, but you have to go back and you have to refactor. Red, green, refactor, commit, test-driven development. Okay, so at this point in this function, order struct list, which isn't called anywhere yet, what I'm going to do is I might actually test this function individually. Yeah, I think I will do that. I'll test this function individually. 30 func. Gonna move down here. Auxiliary functions, I guess, something like this. Func test order structs. Take some t, testing.t. Star, isn't it? Yeah. Order struct list. What do we? No, yeah, I guess we have this one test case to go off of. And the way we can kind of get it to work is to just return struct list. Not from struct to valibot. I think before we call this, we go order struct list. Okay. Ordered struct. I think it is ordered, topologically ordered. Ordered struct. No, but that's the same. New struct list. Really terrible names. I can't come up with good names right now for some reason. And then we get error. Change that here. New struct list. If error is not equal to nil, then we return this and the error. Good. You should still fail. But only the one should fail. Okay. ordered struct list. Here we're actually going to want to call our topological order, which is here. I guess we do. We don't really want to export any of this, so just topological order will be fine. Topological sort of the nodes, return string. Struct list is a map. No, it's not. It is, yeah, it's an array. So what we'll do for now is create a new one. We go an ordered list, which is make of struct list with a length of struct list. Ooh, heap allocation there. And then we go ordering error. Does topological sort even return error? No, it doesn't. It's a perfect function. Return gives me nodes. Yep. And I guess up here we can make a node list, which is make of an array of pointers to nodes. At the bottom we can go node list, append the node, node.node, that's it. Now we have a list of all of the nodes. Great. We can then pass the node list. Okay, types are all good. The ordering, and basically now we want to go through this string, and this is going to be very inefficient linear search. To do, make it better. Generally make this whole function better, actually. I think it's kind of a mess. But what we want to do is we want to go for underscore n in the range of ordering, and then we got to search for that node. Is there slices dot search? No. And it returns the first index. Yeah, I think so. Of the struct, which is ordered list, and then we do func that takes in n of I guess star node. If I return I dot name is equal to n dot equal to n. Yes. What is this then? What? Does not satisfy. Why not? Okay, never mind. Thought we could cheat a little bit. Index is -1 for the range of, so n is one of the structs we want, right? So we're gonna have in the range of the ordered list, node list, if o dot name is equal to n, then index equal to I, break, if index is equal to -1. We actually panic here. Could not find. Yeah, we can return struct list errors dot new. Could not find index of node. And then once we do find that index, we go order index. We go ordered list at the order index is equal to the node list at index. Struct list. Oh, you're not a struct list, are you? You're oh, I don't want to go into node list. I want to go into struct list. Yeah, that's right. So go over not load list but struct list. And your S, yeah, it still works. Struct list at index. Ordered list. And yeah, we're creating memory here again where we could alter struct list in place. We could mutate. Generally this whole function is very inefficient. I'm actually going to make a note of that. Here. Turn a topologically ordered list of structs. This function is ugly and quite inefficient. Much room for improvement. But okay. Our test case doesn't pass because we are violating some memory somewhere. And we are doing it in topological.go line 36. Really? So it goes. And then in this file it goes 53. Yeah, that's DFS call, and then 36. Really? N.visited? Why are you crying? Was it because n is nil? Oh, we got null pointers. How and why? We have some null pointers. I thought that these would be okay. I guess not. Is it because this is stack allocated? Might be. There is a make function. Make in the node make of node. Is it create? No. Make Golang heap allocation of for struct. New. Yeah, it's new node. That should, yeah, that gives me a pointer. And if we go in a node dot name equals s dot name, edges is equal to make of pointer to node 0. And here we go in a node. Doesn't look like that was the problem. Yeah, now we're failing in other test cases as well. Test multiple simple structs. Golang testing, run only one test. Run a single test. Dash run, yeah. Go test dash run. Test multiple simple struct. So multiple simple struct goes hello and it forgets about somewhere along the line stuff is dropped. Okay, let's just do a sanity check and a length of ordering. 2, 1. Why? The length of the ordering is smaller. Oh, because they're disconnected. Didn't account for this in test case. For topological ordering, what if you have disconnected graphs? Func test disconnected. Testing T. Let's grab that one there. Not T.skip. Oh, is that always there? We don't know if they were passing or not. Run test disconnected. Okay. 2 and 1 B. Sorry. Okay. Yep. Right, and it's very true. If you have disconnected graphs, this wouldn't work only if the graphs are fully connected. So what do? Topological order on disconnected. If topological sort uses DFS, how can it succeed with disconnected graphs? On every node, if one of the children is already visited by previous DFS, colored black, then it is already pushed in the outer vector. You know what? Okay. Topological sort Wikipedia. Okay, DFS algorithm. Empty list that will contain the sorted nodes, while exists node without permanent mark, do. Okay. Select an unmarked node, n, so that's the visited, and then we visit that. And we visit them all. Remove temporary mark from n. Is this for cycles? Like the text cycles or something? No. Mark n with a permanent mark. Oh yeah, this is for cycle detection. We don't need we won't need this. We could add it later. How is this different from mine? I think it must be this here, right? While exists node without a permanent mark, do this. And mine does something dumb. So let's try it again. So we go. Func has unvisited node. Nodes node bool for n in the range nodes if n dot visited, if not return true, return false. The word is quite precise there, has unvisited node. While has for has unvisited nodes, then we want to select an unmarked node n in the range of nodes if n dot visited, if it is not visited, then want to DFS n. And then we want to pass the list, I guess, and DFS is going to have the list string, and you pass, and I don't think we need to remove duplicates anymore because that was just me being lazy. And we can do longest here. Oh, this might have to, I'm not sure how Go does this, if it copies an array or not. We'll see. And basically here, if n has permanent mark, then return. Oh yeah. If node.visited, return list. It's one of the base cases, yeah. And let's ignore the temporary mark. We assume it doesn't have cycles. And for each node we visit. Oh, and we don't even have to worry about this here. And we, oh wait, hold on. We don't need this anymore. We just do DFS on node and we pass in the list pointer to it. And then at the end of that loop, yeah, we mark it with a permanent mark. And we add the, don't need that. Nice, yeah. Then onto the list, the node.name. And we return list. Great. Okay. I don't need contains, I don't need remove duplicates because that's just being weird. Yeah, this is much nicer. We put the if on a base case instead of inside the loop, and we just append at the end onto a list that we're doing, and we kind of shift some complexity over to the top function because we have to check if it has unvisited nodes. But you know. Go run specific test file. I can never remember how to test package name. Oh, but yeah, whatever. Okay, that was an infinite loop, right? if it has an unvisited node. Yep. Yeah, this should return pretty quickly. Okay, this should be fine. I wonder where the loop actually is. Is it there? It's probably not. Not sure what's going on here with the test. Pretty weird. Pretty weird. I wish there was a better way to do like test skipping properly. Actually, if I do dash run test single, I can get something. But I do need to print some stuff. So DFS here. Oh, come on, man. Why are you not printing? Okay. Is it just, so it prints that, never reaches that? No, it does. Many times it does. So it goes for, also has unlisted nodes. Oh, is this it's a pointer error. To a pointer. This might be. Nope. Star, the address, yep. Star, the address, yeah, because we want to mutate, and go might be helping us a bit too much by copying memory instead of the pointer. Maybe. Not sure it does that with they might do that with structs. I don't know what happens with arrays. Alright, so what's going on? What? Oh, is it over here? Star. There we go. How is that? Okay, well it passes though. And I think then it must be doing what I think it's doing. It's not a, it's going to be a pointer to an array. not an array of pointers, a pointer to an array. List start, yeah. The address. Yeah, that's it. So we learned a couple of things actually that we weren't so sure on. Go passes slices by value. It will copy the entire slice because you know, as soon as I do pointer to a slice, then it worked. But if I did pointer to, no, sorry, just slice, it would copy, which I wasn't sure it did because not all languages treat arrays like values, but Go does. Same with the structs. That is very, very useful most of the time when you don't have to do mutations, but here we do. Great. So now let's just do topo low. That's great. Just test. Just go. Test. Topo. I'm just going to write topo in all of these so that I can do the search and just run this. Surely you can run a single file, but maybe you can only run a package. Test topo. Test topo 2 doesn't work. Why? Slices are not equal and the test order is, yeah, I mean it's wrong. Quite wrong, I guess. Oh, it's kind of interesting. We do, if I didn't do this here, would it pass? Huh. Oh, it's because now we're doing values. So if I need to do n1.visited is false, I need to basically reset. Perfect. Fix much better Wikipedia powered topological sort. Yeah, that's much better. It was fun to do the algorithm by just top of memory, but no, doesn't always work. And the thing that is nice is the disconnected one worked as well, so that's good. Now we can we run all the tests? No, this one still fails. The test multiple simple. Dash run test multiple simple struct. Oh, you do pass. You do pass, but not always. Yeah, sometimes. Oh, that's so weird. Yeah, you notice it goes also simple struct and simple struct. It's not deterministic. It's not deterministic. Why? Node map, because I'm using node map here. Yeah, I think it's just the map again. So node with index as an index. Can I just make an array of those? Because it will have the struct name inside the node, so maybe it's not that bad. Node map node. Yep. But now, yeah, I need a linear search here. Yeah, okay. This is very, very bad. But again, see if it works. Yeah, so if this is equal to field.name. We append end.node break. Let's say reached equals false. Reached equals true. If not reached, then return struct list errors.new. Could not find struct. And you should be could not find struct. Oh. Am I thinking about this wrong? Potentially. So we go through the node map, and basically we're appending edges, and we're going to look for slices.index returns index of the first occurrence of an s index func. Let's search through node map where the function of n, which is node with index, return n.node.name is equal to field.name n node index node map at the node index node. Wait, what? This is, oh wait, this is a struct name, maybe not a field name. Oh yeah, fnt.println node map, which is not so much a map anymore, is it? And for that we're going to do field.name, at which point it should be a struct name. Nested. Oh, is there I think there is a way to pretty print structs, isn't there? Is it plus v, like that? Yeah. Ish. At which point the index is stupid now. So we don't need node with index anymore. We just need an array of pointers to nodes. Oh, let's get rid of that. Yeah, look, the code is simplifying itself because I'm being silly. There we go, we make the nodes. So we go through the nodes, to all the nodes, and then through all the fields in the node, no? Why am I doing this? Can't I just go node dot? Oh, yeah, I need to kind of, yeah, I see. But I can go struct list at I dot fields. That should work. Simplify this a ton. There we go. Okay. I think 16 I can get rid of. I don't need you. Test nested structs. Is that the only one that fails? Test nested structs, okay. Dash run test nested str. Because it gives me nested, right? And here let's do fnt println n.name. One of them should be nested now. Oh, it's not field name, it's field type. Yeah, that was it, I think. Cool. Yeah, pretty ugly here. We have another O, and it's just going to be cubic complex. Oh, God. That's not great. We'll simplify. And then multiple nested structs still fails. Oh, I guess. Yeah, because wait. So that's the output. Their lengths are the same, but I'm going e object world woo const c, which is an object, hello string a e, const is an object, a string, b goes to c, d goes to e, and yeah, looks identical. Object, boolean, then number, and then string. Yeah, perfect fit, working topological sort during parsing stage. Okay, nice. So now we have, there we go, we have our main function parse, 4 auxiliary functions. These could be tested individually, and probably should. I think this can also move, right? Because all I want is a struct list. I'm going to make another function called get struct list from AST, which is going to give me a struct list from an AST decl. Actually, let's give it a pass file. File which is ast.file. It's going to return a struct list or an error, probably. And here I'm going to take this struct list, make struct list 0, file.declarations, struct list here, return struct list and nil. List error is equal to get struct list from AST, pass to file. If error is not equal to nil, return this and the error. Okay, all is working. Refactor, grabbing struct list from AST, extract it into our own function. Great. Yes, so we get the list of structs, we get the ordered struct list, and then we output structs to Valibot. And that's all good. What else is there to do now? We have all our neat functions there. I mean, we should improve the code, especially for this ordered struct list. I think the Valibot, is this okay? I mean, it looks ugly. But yeah, I think this bit could be improved. Right, to do. Can use, but this is the thing. If you don't have that many, we're never gonna have that many validators imported, I assume. So this would be a bit. This might be slower if you use a map, right? Because of the hashing functions taking a while, even though it is constant speed. But definitely order struct list needs to be better. This is a mess of a function. Okay, well, we have our test cases, and it all seems to work. There are many things to do still. Currently, we still only have, we can nest structs and stuff, But we don't support, what's the other? We don't support embedded structs, like type B struct hello string B. So if I do var, if I do a x, this has to be inside the body of a function. X, which is a, we're gonna have b, which is gonna be b. Oh, is it? I thought this would be embedded actually. Golang embedded structs. How do you do this? Struct embedding. So we have base and then a string. And we do base there. A container embeds a base. An embedding looks like a field without a name. When creating structure literal, we have to initialize the embedding explicitly. Here the embedded type serves as the field name. We can access the fields directly on, oh, is that, okay, so if I do x dot, we can do b or hello directly, right, I see. But this doesn't, ooh, what should the output of this be? We should have both, right? We should be able to do x dot b dot hello and x dot hello. We should definitely allow for both, right? But it kind of depends on how they are JSONified. Right? Let's test. Let's go into main and actually do some of this. So I have x and we do JSON string. We can ignore the error. It's just JSON.Marshall x fmt.print line the string. Actually, if you do JSON string of JSON string, there we go. Go run go. Hello world. Yeah, we don't have access to B, so we're gonna follow the same convention as the JSON Marshall and embed the fields and not have B there. So neat. Okay. That will definitely complicate things. But, okay. Okay, func test embedded struct. So let's let's copy everything here. Let's just have a have hello, and then we'll have type b struct, which just embeds a. It's gonna have const. So first of all, we're gonna need to declare a first, and just to throw it off a little bit, I'm gonna put it there, put b above a. A is just going to have hello, a string directly, nothing else. And we're also going to have b, and b is also going to have hello string, like so. And go run, go test dash run test embedded. Fails. More than one name returned, because we don't deal with this very well. Here, type b struct. Because what this really is a, but it's embedded. and so it's quite different. We might need to be able to tell our parser that. So first of all, where is that error? More than, okay, struct ast to list, more than one name. So actually it should be bigger than, and we should say if the length of l.names is bigger than 1. Then we say if the length of l.names is equal to 0. This is embedded struct. And this name type, I guess we could have embedded boolean to say whether it is embedded or not. We do this. A name type, which is name type. That name type. If the length of l.names is equal to 0, then name type.embedded is true. Okay, that's quite explanatory, self-explanatory. Let's run all the tests. Nothing fails. Oh, test embedded struct does fail. Oh, because of the field name up there. Okay. Length of l.names is equal to 0. Field name is equal to this. Else this. Field name is equal to well, not l.names, but l.type. No. Okay, we do one there. 0. We're gonna do field name is equal to the field type. We're gonna print name type a true, and then hello string false. Print line embedded. So we do we don't just do field name there. Oh, we do name type dot name is equal to the field type. Yep. A and an A. And that kind of did some of the trick, right? Because we have const b object and it tries to go A, but because it's embedded, it should flatten it instead. Okay, that's enough for struct ast. Do that list there. Now, could we maybe do some thing a bit clever on Validators? No, let's not. I was wondering if maybe we could do the clever part on the JavaScript world, but let's not. What we should do here instead is alter the fields. So we have struct ast to list. Yep. And we have order. Struct fields come from struct ast to list. which is where we just were. Maybe actually we shouldn't append anything in this case. And we should treat it differently. If the length of L names is 0, we are embedded. So we should basically continue. And we can get rid of this. You can get rid of this. And you can do this. Okay, things just work a little bit better now. And here we're going to have to go through the, like recursively, we're going to have to go in and go my nested fields is going to be oh yeah, okay. AST fields is going to be slices dot equal with a function with AST structs with func of AST, which is going to be pointed to an AST dot field, and it's going to return true if return AST dot the field. What are we trying to do? We're trying to get the AST node for the original, but this is only fields, so we can't. We need here we would need the list of all structs, right? Because yeah, this gives me only one of the structs. So what I would like is an array of struct types. Okay. We could reorder this function as well to do all these checks beforehand and give us the yeah, we could, maybe, should. Okay. Let's do this first. Let's make AST structs, which is going to be an array of pointers to AST.struct type. And then here we do AST structs equal to append of struct type. Okay, and then what we'd have to do is for underscore s in the range of AST structs. Then we do this. Wait. Oh, does a struct type not have a name? Yeah, I guess not. Oh yeah, because it's just, okay. So maybe we go and do type struct with name. Struct which is embedded of the struct type, but with a name as well. So we're going to do an AST to array of struct with name. Struct with name. Just going to have name of struct, not struct type, but the type def AST node. And then struct type, which is going to be struct type. Name.name. That's it. And then here we can go s.name, s.fields, yeah. We don't need that, to be fair. Just this. Great. Do you still run? Yeah, good. Just the embedded struct doesn't. All right, we did some rejigging, and here we can have a look at all AST structs, which is going to be a list of the type that we defined above, struct with name. Okay. And then here we can go AST structs, and yeah, what we're going to do is we're going to search through these to find the name of the struct that we want. We're going to get its fields. Oh, there is a way of doing like a double pass here and kind of marking the embedded ones to be worked on later. And this would be, I think, more efficient because otherwise you're doing double work on some of these. But okay, all AST structs, which is going to be a struct with name, AST dot where the name is equal to just the type. So let's define these above here, and then also this one here, and really that should be there as well. Okay. AST dot name is equal to field type dot field type too many return values. Why is it too many return values? Let's just return this. Is there something with the LSP? Oh, this is equal, not find index. Alright, index func. Yeah, okay. Which is struct with name. Name is equal to field type. Okay. If st field is equal to -1, return struct list. New, could not find embedded struct. Okay. I'm just going to print some. I'm going to print AST field here. What do we get? Could not find a better struct. AST.name. No, not AST.name. Field type. And also all AST structs. Wait, all AST structs gives you B? Should give you more than that. That's not what? That's not quite right. So we go through, yeah, this needs to be even one step out. So let me put this here, and then this goes here. Now it's correct. We get BA and then that goes to 1. Okay. Yep. Yeah, and then B just kind of is returning empty. Cool. Now we get the correct AST field. Index even. And we go, let's make embedded struct is AST field. This is going to be all AST structs at that index. And then what we want to do is we want to say struct field for this is equal to append struct field, and I think we just call this recursively and it will work. Embedded struct fields, I didn't spell that right, and then error is equal to struct AST to list with all the AST structs and embedded struct dot fields. Yeah, and if error is not equal to nil, return struct fields and errors, and then just the error. We lift the error up. This is going to be name type, and that's name type embedded struct fields dot 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 after. Oh, right, that's the syntax. Do you work? Aha, you do work. Very nice. Not passing the test, but why? Does BA? Oh yeah, it should do BA, shouldn't it? Because B is above. And there's no dependency, so. And also just this. Perfect. That's really nice. Let's make it even more complicated. Test embedded struct complex. So we're going to have embedding of multiple. Let's have type A has a field that is hello if float64. B, which is an embedding of just B, C, and then just in between there, let's do world string. Let's do B, which is a struct that embeds C as well, and it has another field, my field, which is going to be Boolean. We're going to have type C, which is struct that embeds type D, and then type D is just going to have hello field D string, and then C is going to embed D, and my num, which is going to be an int. That's quite interesting. Test embedded struct complex. Oof. Yeah. Pretty interesting. Pass line 78. Oh, this is in the order struct list already. What if for now, I'm tempted to just do this. See what happens. So we get this, which I'm pretty sure is correct. Oh, let's double check this. We get the import of object first, then number, then string, and eventually Boolean as well. Oh, but it's going to be bool. Yeah, string and Boolean. Going to have hello, and then it's going to embed B. B is going to embed C. C is going to embed D, which is my field, field D, and then it's going to be my num from C. It's going to be my field from B. is Boolean. It's going to have world string and then embedded C. C is going to embed field D string my num. Great. That all works really well. And then B is just going to be embedding of C, which is embedding of D. So field D, my num and my field. And then this is Boolean like this. And then field C is field D string number, field D. That's awesome. Yeah, I think it actually works really well. But we do have a problem here. Wait, we should have a problem here. We had a problem there? Okay. Cool. Yeah, I mean, I didn't see how that. Testing more complex case for embedded structs. Oh, I don't really know how this deals with namespacing. Like model dot. That might have some not great consequences. But super cool. I'm getting it to work really well. Let's do that test case that I meant. Test even func name spaced test name spaced. Yeah, just structs. Let's go for a simple one. I can't really namespace structs on a single file. Yeah, so actually I can't test this. But one thing that would be interesting is to have the AST go ahead and actually look for the definitions of other structs. So we'd have to do parsing of multiple files, not just the one. But for now, you work. Calling it a day there. Alright, thank you for watching and see you in the next one.